Hopefully you got this all figured out with the equations. So why are we talking about light? Why are we talking about energy when we're talking about electrons? Isn't that what this chapter is about? What you're going to see, and I'm giving away the big surprise here, as you go through the chapter, electrons are waves and particles. And all of these calculations that you do for light or energy also can be used for electrons. Electrons can be measured in terms of energy and or mass. So they also do something else that's very, very interesting and initially unexpected, is not only do they act as waves and particles, they also will absorb and release energy from other sources. So that other source could be heat, it could be electricity, it could be a chemical energy source, it could be light, it could be all different kinds of energy. But they can absorb or release this energy, and when they absorb it, they will release it at specific wavelengths, and sometimes they're in the visible spectrum, which means we see the light as color. And we see the object as having color. All right, so this is what went on. In the early 1900s, scientists recognized that passing an electric current through a closed tube containing only the gas phase of one element produced specific colors unique to each element. They called it the atomic emission spectrum. So see here, the helium is like this purpley color, and so is the argon, but you can tell it's a different shade. It's a different look to it. We have the neon, we have the krypton, and we have the xenon. But they did these for all the elements. They messed around with everything. It was the cool thing to do if you were in the early 1900s and a scientist. And everyone was trying to understand why every time you put neon in a tube, anywhere in the world, it always came out looking the same. And then what they did was they took polarized film, which is, you know what polarized sunglasses are like. If you don't, they are wonderful and you should check them out. But polarized film will take a series of wavelengths that are all coming off, so you're kind of seeing a combined color, and they will split them into the exact specific wavelengths that are making up that color. And it turns out that every element has its own unique little wavelengths associated with it. So if we go ahead and we look at the spectrums, and these aren't the exact same spectrums as in the pictures up here. This is just what we could find a picture of. Sodium would be giving off a certain color, but when they polarized it, they could see that it had two wavelengths here, two wavelengths here, two wavelengths here, and two wavelengths here. When you combine those together, you get that color that you're kind of used to seeing. And it would do that every single time. A little bit of energy, a lot bit of energy. It would do that every time. Hydrogen would always break up into these wavelengths. Calcium has a lot of them, and mercury has several. And so the scientists questioned, why is it that these wavelengths, which are, they actually can let you identify elements that are in there. Why is it that they are coming up the same way every time, regardless of the energy we're putting in? And why are they always coming up the same time, with the same exact wavelengths every single time?